Soil hydraulic conductivity is one of the important soil physical properties which tells us at what rate the water moves through the soil. It indicates the permeability and texture of the soil, and it further helps us in planning, irrigation and drainage management. In this video, let us learn about determination of soil hydraulic conductivity using constant head permeameter. Materials required for determination of soil hydraulic conductivity: constant head permeator, core soil sample, measuring cylinder, 500 ml glass beakers, and finally stopwatch.
First, let us understand about the constant head permeator assembly. First, there is a steel disc in which we have to place the funnel. This funnel is placed here to facilitate drainage during the experiment, and above the funnel here we have to place the perforated steel disc which prevents soil loss during the experiment. In this perforated steel disc we have to place the core sampler, and below the core sampler we have to tie the filter paper, and above the core sampler we have to place the overhead water supply system and tie it with the tape so as to avoid water leakage. In the overhead water system, there is an inflow valve and outflow valve. The inflow valve is slightly lower to the outflow valve, so a 2 to 3 centimeter water stand will be established during the experiment. The water is supplied to the overhead water system through the overhead tank, and water is supplied to the overhead tank through the tap.
Tie the filter paper at the bottom of the core soil sample and saturate the core soil sample in a tray containing water overnight and allow it to saturate. After overnight saturation, take out the core soil sample and place it over the funnel in the constant head permeator. Connect the overhead water supply system with the core soil sample and tie it with the sellotape.
Now this assembly is ready for doing this experiment. Now let's open the tap. Water then flows from the tap to the overhead water system. As the overhead water system is filled, it will then move towards the
water is then supplied to the overhead water supply system through inflow valve. After saturation of the soil sample, the soil then conducts the water. The water then percolates down through the soil sample and through the funnel and gets collected in the beaker. After 20 minutes, take out the beaker and place a new beaker inside it. We have to do this for 60 minutes and record the observations. After collecting the filtrate in the beaker, measure it using a measuring cylinder and note down the volume of water collected. After collecting the filtrate in the beaker, measure it using a measuring cylinder and note down the observations for every 20 minutes and continue doing this for 60 minutes and note down the observations, and finally find the average. Here it comes to 100 mm. From this observed values, the soil hydraulic conductivity is calculated as follows. First, convert the given data. Length L is equal to 5 cm, which is nothing but length of the soil sample, and diameter is equal to 7 cm, which is the diameter of the core soil sample, and radius is equal to 3.5 cm. Head difference is equal to length of the soil sample plus the standing water, which is 3 cm. So 5 plus 3 is equal to 8 cm. The water collected average is equal to 100 mm. Convert it to centimeter cube. Here it comes to 100 centimeter cube. Time is equal to 20 minutes, which is equal to 1200 seconds. Calculate the discharge Q and area. Q discharge is equal to volume in centimeter cube divided by time in second is equal to 100 divided by 1200, and Q discharge is here is equal to 0.0833 centimeter cube per second, and the cross sectional area is found using pi r square formula, and here comes to 38.465 centimeter square. Hydraulic conductivity is calculated using Dox's formula. K, soil hydraulic conductivity in centimeter per second is equal to Q discharge, its SI unit is centimeter cube per second, into length of the soil sample in centimeter divided by A, cross sectional area in centimeter square, into head difference in centimeter. From the observed value, the soil hydraulic conductivity is equal to 0.00135 centimeter per second. It should be converted into centimeter per hour by multiplying with 3600. For our soil sample, the soil hydraulic conductivity is 4.86 centimeter per hour. Now, interpretation. When hydraulic conductivity is less than 0.125 centimeter per hour, it comes to extremely slow permeability. The soil has higher clay content and it has surface crust and subsurface hard fan. When it is between 0.125 to 0.5, it has very slow permeability, and when the hydraulic conductivity is between 0.5 to 2, it has slow permeability and has moderately high clay content. And when the hydraulic conductivity is between 2 to 6.25, it comes to moderate permeability and has loamy textured soil. When hydraulic conductivity is between 6.25 to 12.5, it has moderately rapid permeability and sandy loam texture. When the hydraulic conductivity is 12.5 to 25, it has rapid permeability and it has porous textured soils. And when the hydraulic conductivity is more than 25, it has very rapid permeability. Our given soil sample has an hydraulic conductivity of 4.86 cm per hour. So the soil sample is loamy textured and with moderate permeability. So our given soil sample is suitable for most arable crops. In this video, we have learned about the determination of soil hydraulic conductivity using constant net permeameter. Hope you would have understood, and thank you for watching this video.